I'm Dmitris. I'm a cryptography researcher at Nillion, and I will present today the joint work with Mehmet Ugurbil and Miguel de Vega from Nillion, as well as Charles Gert and Nektarios Tsoutsos from the University of Delaware. The title of this work is Ripple, Accelerating Programmable Bootstraps for Fully Homomorphic Encryption with Wavelet Approximations. So we talked about homomorphic encryption before, but let me do a brief introduction. With homomorphic encryption, the way I like to think about it is that it enables a new paradigm on computing on encrypted data, and that is on the client-server model, where we have the client, and they have some data, they encrypt them locally, they upload it to a cloud service provider, which can run some computations without looking at the data while the data remain encrypted, and send back an encrypted result. Now only the client can decrypt it and figure out the result of the computation. What's interesting about homomorphic encryption is that it enables many use cases that are hot right now, like privacy-preserving machine learning. You know, we have heard about ChatGPT and the encrypted variant of ChatGPT that we want to use someday, where our queries, we encrypt them locally. We upload our encrypted queries to a ChatGPT-like service. They generate an encrypted result without even looking at our query, and then we get back the answer. Another prominent use case is private transactions, where we want to put transactions on the blockchain and protect the amounts that we send and receive, and not only that. This is all very nice. However, we don't really talk about the problems with homomorphic encryption. And one of them is that evaluating nonlinear functions is very problematic. Some schemes, although they come with native additions and multiplications, they don't expose any capability of evaluating nonlinear functions directly. For instance, we cannot easily compute a logarithm or a square root and so on. Of course, we can always create these nonlinearities and express them as Boolean circuits. However, this won't be very efficient because the circuits will be big and the evaluation will be slow. On the flip side of things, we have schemes like CGGI. Many of you might know it as FHE, where through this technique that's called programmable bootstrapping, we can now evaluate lookup tables. And what is a lookup table? Imagine that we take a function, and for many different inputs of this function, we essentially get the output. So we have a lookup for different inputs, we get different outputs. And this is great. However, as we go to higher precisions, we require larger parameter sizes, and then the lookup tables start to become slower and slower. On the flip side of things, a very widely used technique in fully homomorphic encryption, and also MPC as well, is to quantize our inputs. And quantization in this case means if we start with the input x, which is w bits long, then we can just truncate some bits, remove the least significant bits, and now we end up, let's say, with half the bit size, and we can now evaluate a significantly smaller lookup table, which is quite efficient, but unfortunately not as accurate. This yields higher errors. And this is where the Ripple framework comes in. The idea is to evaluate smaller lookup tables and maintain high accuracies. And we do that using the discrete wavelet transform, or DWT, which is a technique that comes from signal processing. So today, what we will see are two protocols that rely on DWT, and these are the two families, HAR DWT and bi-orthogonal DWT, and how we have created these protocols specifically for full homomorphic encryption. There are some trade-offs between the two of them, namely HAR DWT is significantly simpler than the bi-orthogonal DWT, and thus faster, but it does not compress as well, so it has higher errors. And on the flip side, the bi-orthogonal is significantly more complicated and thus slower, but achieves greater approximations. I will briefly talk about both of them, but for the details regarding the bi-orthogonal, because as it's more complicated, I will refer you to the paper. Lastly, we will see how using these two DWT families, we can bring the error downs in many nonlinear functions, widely used nonlinear functions in machine learning applications, and also a set of benchmarks. Starting with DWT, we can think about it as having an initial signal. And now if we were to represent this initial signal S as a lookup table, this means that we can take many data points across the x-axis, and for each of these data points, we get an evaluation at the y-axis. And the more data points we have, of course, the better that we can approximate this initial signal. So the idea behind DWT is that we can actually split the signal into what's called an approximation coefficient and a detail coefficient. And each of these the two new signals have half the data points of our original signal. And now what is interesting is that if we do that again by treating the approximation as the new signal, then we get a new approximation and new detail coefficients, and so on and so forth. The realization of this work and what we have observed is that after we have applied multiple DWTs, the smooth part of the approximated signal has remained very similar to our initial signal. So it has this pattern, right? And although the small details are missing, we can get a still very good approximation. And it's in certain functions, we can actually get rid completely of the details. And effectively, what we have achieved now is that with each DWT application that we have done, we have halved the number of data points that we need to have in our lookup table. So going back to our original goal, to evaluate the lookup table, let's say that we have 32 bits, and we want to evaluate the lookup table over X, which is the 32 bits long, and get a Y value back, which is also 32 bits long. So we can actually not do that, so we need to approximate this. Because as we mentioned before, evaluating a lookup table over 32-bit inputs is quite inefficient. As a matter of fact, we tried this with TF-HERS, and to generate the lookup tables, like 30-bit lookup tables took over 15 minutes on an AWS server, and 32-bit lookup tables went over an hour. And of course, the problem here is not the library, right? The TF-HERS state of the art. The problem is that what we're trying to do, to encode all these 2 to the 32 entries, is quite silly. Too many possibilities there. So what many works do as a result is to quantize the input. And this is what we saw before. So starting with 32 bits here, we go down to 16 or to 20, depending on the application, and we end up evaluating a smaller lookup table, which is way more efficient, but it's not as a good approximation, because in this case, the result is also like 16 bits, it's not 32. With Ripple, and we have the hard DWT and the bi-orthogonal DWT. Let's see the hard DWT first. In this case, again, we start with W-bit inputs, 32 in our example. We truncate it down to 16, but now what we do is that we evaluate 2 different lookup tables. Each one requires 16-bit inputs, and we get the least significant bits and the most significant bits, and then we concatenate them. And just by doing that, intuitively at least, you can see that we end up now again with 32 bits. And these are not any random lookup tables. These are DWT encoded lookup tables that represent our function. And since we are already like on W bits instead of 16, we can achieve a significantly better approximation this way. On the flip side of things, with bi-orthogonal DWT, this is way more complicated, so I won't go into the details of that. But the message that I want to pass across here is that in the previous one, in HAR, we only worked over half the bits, and we evaluated the lookup tables, whereas here, we split our input to the most significant bits and to the least significant bits. With the most significant bits, we evaluate 2 lookup tables, and with the least significant bits, we do some scalar operations. And you can see, at least intuitively, that now since we work over the whole input and end up also with W bits as the output, then this compresses better than the hard DWT, because hard gets rid of the least significant bits. Another thing that I want to point out here is that this lookup table is configurable. So if we choose to put it as the same size as in the har, which is 16 bits in our example, then the runtime of bi-orthogonal will be quite slower, but it will achieve lower errors. Whereas if we make j smaller and smaller, then this will become faster and faster. But the errors will go up. And this is a trade-off that we will see later on as well. Going to some nonlinearities, and these are famous functions or well-used functions for machine learning, like square roots, reciprocal, and so on. You can see with the blue lines that we have the simple quantization approach that is always higher, and higher in this case means worse because it has higher error. And on the x-axis, we saw how the errors go down when we increase the lookup table sizes. So the next one is hard DWD, which is always almost 1 order of magnitude better than the quantization. Then we have a DWD family that I did not talk about, which is the DB2. And we experimented with that, but as you can see here, it's always worse than the bi-orthogonal DWD, but it's more complicated to implement, so it's not very efficient. And for that reason, we focus on the bi-orthogonal DWD, which achieves the best compression out of all these options. So to further optimize things, we observed that some functions have two very interesting properties. And these two properties is the first one, some functions have a symmetry point, which means that around this symmetry point, and on the left and the right of that, the function has the same behavior, but it's flipped. So you can see here that this part is the same as this part, but just flipped. The second property is that outside of the bounds x left and x right, like this part and this part, the function starts converging into some values. So we can take advantage of these two properties and further reduce the size of our lookup tables. I will start with the second property first. And the idea is that we can create our lookup table only for this part of the function and do an encrypted comparison to see if we are within the bounds x right and x left. And if we are outside, we will just use the fixed value that the function converges to. Otherwise, we will look up the value of the function. And this already achieves a better approximation because instead of having to create one lookup table for the whole function, now we only have to create for a certain part of the function, so we can get more data points there and approximate the function better. With the second property that is symmetric, we can further reduce the lookup table size and only encode this blue area of the function, and essentially based on whether we are on the left or on the right of the symmetry point, we can flip these values here. And by doing that, we can see that for sigmoid, the error function, hyperbolic tangent, and so on, for different lookup table sizes, 12 and 16 in this case, although we have achieved a very good approximation already with the hardened bi-orthogonal, this optimization further brings down the errors. And in case of the har, the errors vary from 30x to 500x, like lower errors. And in the case of bi-orthogonal, it goes from 2.2 up to 147 times lower errors. And in har, this optimization has a significantly better effect. And the reason is that bi-orthogonal already achieves a very good compression. So this is a slightly more technical slide, but I want to show you how important it is to be clever in some applications with FHE and not to take the easy way out. So in this case, I want to focus on the correlation coefficient. And we have an application where we have two vectors. A client has a vector u, and the server has a vector v. And we want to see how correlated these two vectors are. An example is, based on years of experience, let's say the vector u, how the salaries of individuals change. So if these two grow in tandem, then this means that they are correlated, so the correlation coefficient will go close to 1, and if they are inverse, then the correlation coefficient will go towards -1. So we need to compute this function, like the covariance, and then the two square roots. First of all, we observe that some things the server knows already, so they can be on plaintext directly. The next thing is to compute the encrypted covariance, this part, which can be done with normal homomorphic operations. Then we compute this part without the square root. And finally, we can create our lookup table as a scale, S, divided by the square root of x times this plaintext. Now, if we pack everything together, we don't have to create different lookup tables, for the square root or for the reciprocal and so on. Like, we can create one lookup table and further accelerate things. And we can use what we computed in step 2, this thing, to actually look up the value and end up with a correlation coefficient. As a baseline, and for different vector sizes, but this specific one was 18 seconds. And then with the hard DWT, although achieving lower errors, we brought this time down to 15 seconds. And with the biorthogonal DWT, using the same sizes of lookup tables, then this was slower than the baseline, but achieved, again, lower errors. Then focusing on a logistic regression application, I want to point to these first three. So the blue is the quantization, which is always the fastest. And that makes sense, because it just truncates half of the bit size. And then with the hard DWT, it's as fast as the quantization, but the errors are significantly lower. And for the biorthogonal DWT, this is the trade-off that I was talking about earlier. We see that it's always slower than the hard, but it has lower errors. And for bit sizes bigger than 24, even the biorthogonal DWT, which is the slow version, is quite fast and faster than the related works. As a future work, we would like to explore how we can actually use different schemes like CKKS for the linear layers to further accelerate this, and then switch to CGGI or FHE to evaluate the DWT encrypted lookup table. This way, we can get the best of both worlds, because we will get the fast evaluation from the linear layers, and then we will also get the fast lookup table from CGGI. And two libraries that can be used for that would be like OpenFHE and Latigo that already implement various schemes and scheme switching. All right. I'll shift domain a little bit, and we observe that this core idea of a lookup table can also be used to other domains, and namely this can be used to MPC. And MPC has a very similar problem as FHE, in that non-linearities are very difficult to evaluate. So many works, what they have been doing is that they are trying to do polynomial approximations, which end up being very expensive and sometimes also inaccurate. There are many prominent works the last 2-3 years that focus on secure lookup table evaluation under MPC, and taking ideas from this work and the idea of Ripple, we can create, and we have created the kernel framework that essentially achieves lookup table evaluation under DWT in MPC, and we have reduced the communication, we achieve faster evaluation at the same time, and we can go and evaluate even LLMs under MPC, like GPT-2, BERT, the 3 BERT models, in a matter of seconds. All right, to wrap up, lookup tables are very important for full homomorphic encryption and also MPC. However, we have to be very careful on the way that we use the lookup tables, because as they grow larger, they require bigger parameters. And although quantization has been a widely used technique in both areas, quantization can incur high errors. As a result, we have seen that with Ripple, we can reduce the lookup table sizes to bring the times down, and also at the same time achieve lower errors and reduce lookup table sizes. And an interesting side effect is that this can also be generalized to other works further, and as we saw in curl, which is an MPC work that we will be publishing next week. Yeah, that's all. I'll be happy to take any questions.
Any questions? So I guess the bigger the table lookup, the better the approximation. Because you're effectively extracting the relevant signal from that. Does that mean that it's going to work better on, I would say, like table lookups with obvious patterns, let's say as sinusoid or something, versus a table lookup that encodes some very difficult function?
Yeah, that's exactly on point. And that's what I mentioned earlier about the smooth functions. So if your function is completely random, it's not much like the DWT can do. Like you will start losing the details as you compress more and more. And this is an example of it. So this is a smooth function, I would say. And if we didn't do this trick, like the lookup table would have to be over the whole domain of our function. Now, let's say that we have 20 bits, right? 2 to the 20 possible lookup table entries. So it would be different to encode a big domain, and it's different to encode like the small domain. Now we have the same size of lookup table to encode like a smaller area, so we get a better approximation. And as we bring this down, we get better and better approximations.
And so using that versus, let's say, using a more granular, way of representing the function. So for example, if I took that function and I represented it as an 8 value table lookup, I just basically create small bins at different places. If you compare that to what you guys are doing, have you done any work like that?
So yeah, that's essentially the quantization technique. Oops, sorry.
Okay, so that's what you mean in this case, okay.
Because with the quantization, by chopping off some bits, essentially you create this more granular sizes. And now these are like increased lookup table sizes. Let's say here, for instance, right? And the quantization, it already achieves like a very good approximation. However, if we can do better, why not go for that? And at the same time, like you can see that the bi-orthogonal, like it goes very quickly down. So like the difference here is like significantly big. Now, if we talk about here, you might make the case that using the DWT and having the extra overhead of doing these linear operations, for instance, for the bi-orthogonal, or the 2 lookups instead of the 1, might not be worth it. But if we talk about this area here, it's pretty interesting.
Okay, I see. So I think one area where this would be useful is actually for machine learning, because in machine learning you can tolerate approximation errors. For blockchain, it's a little bit more tricky. If you want to check if someone has enough money to send it, you want to be sure about it. Have you plugged this into TF-HERS already or not?
Yeah, actually in this library, and all the results that I saw were with TF-HERS. It was fairly easy because the DWT process can be done offline. So the only thing that you need to do is where you
encode the table lookup.
Exactly, yeah.
Nice. Okay, this would be interesting to test in our compiler to see if we can get better performance for machine learning stuff, for example. So
yeah,
we can talk about that.
So in the curl library that I showed like in one slide before the end, that was in MPC. We saw that like the difference with quantization like actually started paying off. So like even like in FHE, we expect to see similar results, and based on these tables also we can.
All right, nice. Thank you.
Thanks.
This is especially useful when you do machine learning with sigmoid functions and this kind of things. But if you have relos, it's not going to be that relevant, right? Because a relo is quite easy to encode. It's like the first bit, and then you do like a sweep over the other bits. So maybe I don't know. Like, yeah, I don't know.
I think for me, it's not so much about the small table lookups, right? Right now, the way that we do machine learning in FHE is we literally round and approximate the bootstrapping by cutting off just a bunch of bits. And it turns out that neural networks still work that way. They're pretty resilient, actually. But what I'm interested here is basically that you can get this same approximation with much smaller table lookups, potentially. So instead of using tiny table lookups, you can use bigger one and have, maybe a trade-off performance there, right? This is what you're saying here. You can basically get like a 16-bit quantized table lookup performance with 8 bits, right?
So here I'm not showing the performance. I'm showing the errors on the
yeah, that's what I meant. Yeah.
Yeah. So So for 14 and up, like using DWT does not make sense, right? Because the quantization is almost the same. But going to smaller sizes, and
Exactly.
it makes sense. To answer the earlier question about Relu, so there are some MPC works that do some different tricks, essentially, based on the function. So in some cases, it might make sense to do an encrypted comparison and only do the lookup table on the right-hand side of the function, you know, as the Relu starts going up. And there are other functions that are interesting like this. The DWT, I think it pays more off when the function has like a smooth pattern. But yeah, for functions that change rapidly, like it's also like if we can do DWT plus a small trick.
Thanks. Any other questions? All right, great. Well, thank you so much, Dmitris.